Well, based on my clock over here, I'm 2 minutes after the 12:30. So let's get started. Thanks everyone to joining the Digital Ag, Digital Forestry seminar series. And today we have the opportunity to listen from Dr. Aaron Maxwell. Aaron is an assistant professor at West Virginia University in the Department of Geology and Geography. And he has a wide interest in remote sensing related work, such as land use, land cover change analysis, application of the machine learning on LiDAR, and so on and so forth. And one thing in particular I would mention is that he was the recipient of the NSF Career Award last year. So congratulations, Aaron, on that one. It's a big one to land. Today, he's going to tell us about how to utilizing remote sensing for forest type delineation and field loading estimations. So Aaron, the floor is yours.
Thank you. If anyone has trouble hearing me or anything, just let me know. I have the chat up over on the other screen here, and or you can just shout out if you want. Yeah, so I appreciated being invited to this. It's a good opportunity for me, and I really wanted to come in person, but unfortunately my schedule didn't allow for it. So hopefully, if maybe sometime in the future, I'll get to actually physically come over that way. All right, so I'm going to talk today about two projects that honestly are not related to each other, but I think that they collectively, there's some interesting findings and just best practices and lessons learned from using remote sensing in a forestry and forest fire related context. So I've already introduced, but just a couple notes about myself. Again, I'm at West Virginia University. I'm in the Geology and Geography department. I'm actually from West Virginia originally. My parents still live like a half hour from Morgantown here where I live now. I did my undergrad at a small college in West Virginia. And then I did my master's and my PhD here at West Virginia University. Other than working in the department, I'm the faculty or director for the West Virginia GIS Technical Center, which is basically it's a state agency that's housed in our department, and they do applied mapping, data curation, web app development. It's a really big service for the state, and they do a really good job. And I'm the PI for West Virginia View. You may be familiar with the America View system. So years ago, the USGS wanted to fund programs to increase the use of Landsat and data at the state scale. So America View was created and under that umbrella, and then they fund state views. So we're West Virginia View. There is an Indiana View, for example. And then just broadly, I'm interested in geospatial science, remote sensing, spatial modeling with machine learning and deep learning. And I do some work with forestry, a little bit with wetlands, and I do a lot with geohazard and geomorphic mapping. That's kind of my big thing, which I'm not going to talk about in this talk. So just a couple of things before I get into it, plus the disclaimers we're supposed to put on things. So the first project I'm going to talk about was funded through America View via West Virginia View and the United States Geological Survey, because they're the group that funds America View indirectly. And then the second project related to fire fuel modeling that was funded by the USDA Forest Service and with the Tall Timbers Research Station and WiFire, which is this project right now at the University of San Diego, where they're trying to generate like fire behavior or fire predictive models. So we work a little bit on that project in an ancillary way. And then just a few other notes. The first project I'm going to discuss, part of this was done by my master's student, Faith Hartley, who graduated just here in August. She's now working at the Appalachian Regional Commission in DC. Michelle Bester, who's my current postdoc in the lab. And then my colleagues that I work with at the Northern Research Station, Mike Gallagher and Nick Skoronsky, they're heavily involved in the second part of the second study I'm going to discuss. The first study that I'm going to discuss is this study, and it was published a few months ago in a special issue of Geographies that Russ Congleton ran as editor. So it's an open access if you're interested. And the second study was published in Remote Sensing in 2021, which again is also an open access. Okay, so the first project I'm going to discuss was a forest type mapping exercise. So the goal of this project, which again was partially completed by my master's student, we were looking at trying to map and differentiate broad forest community types at the Landsat's resolution, 30-meter pixels, across the entire state, using a combination of spectral data and terrain metrics derived from elevation data. So in order to conduct this project, we needed ground data, and the ground data were provided by the state's Department of Natural Resources, specifically their Natural Heritage Program. So over several decades, the state and the DNR have been collecting field plots across the state, where they do like soil, take soil measurements, and then look at the vegetation, both the canopy and the subcanopy, and then they maintain this database. So part of that is categorizing all of the stands or plots that they visit into broad forest community types. So that became our data set, our training data and validation data for this project. It was nice that that existed because clearly couldn't do it without it. The spectral data that we use in this study came from GLAD, which is GLAD Phenology Metrics, which is a product from the University of Maryland I'll talk about. And then the elevation data came from the National Elevation Data Set, specifically the 10-meter product. Just a couple notes about West Virginia. We actually have a pretty varied topography and physiographies across the state, and that does kind of affect the types of forests and natural communities that you see. So in the western part of the state, it's dominated by a dissected plateau with a dendritic stream network. There's a lot of oak dominant forests and just mixed mesophytic forests in those areas, with some stands of hemlock. In the Allegheny Highlands, which is the most mountainous high elevation part of the state, we have some native stands of red spruce, northern hardwoods, and then again mixed mesophytic and oak, generally at lower elevations. And then the Valley and Ridge, which is just east of the Allegheny front, is a folded mountain belt similar to central Pennsylvania. So synclines, anticlines, and then like a trellis stream network draped over that. And that's generally the lowest elevation and driest part of the state. So there's actually a good bit of variability across the state in terms of physiography and even precipitation and whatnot. So that was part of the reason we're interested in trying to differentiate these like broad community types. Just try to put this in context a bit. The mapping or differentiation of forest community types has been pursued for a long time. I mean, since the advent of the Landsat missions, there's been work done to try to differentiate forest community types. And more recently, there's been a focus on a few kind of key areas that have shown to be helpful or potentially advance the field. So just kind of some highlights. This is just a list of papers that have investigated these types of problems. One thing that seems to really help with forest type differentiation, especially in a landscape with fairly varied topography or local topography, is to incorporate metrics derived from elevation data. So that's been shown to be pretty consistently useful for this type of problem. Now, just using terrain data in and of itself without any spectral information generally doesn't do a very good job. But if you combine that with spectral data, then it generally does. In terms of the spectral data, it's generally been shown that having multiple images that somewhat capture seasonality or phenology is going to be helpful, as opposed to having a single image, say in the growing season or in the fall or in the spring. People have looked at several different ways that you could potentially incorporate that type of information. One of the simplest is to just simply take the take a summer image, a fall and a spring image, or maybe the mean or mean of the spectral bands across multiple images by season. Another method that's been pursued more recently is the use of harmonic regression, where you effectively fit a model through all the observations that you have available, and then with multiple harmonics, and then grab the coefficients from that fitted function and use that as your feature space to make predictions. And then the other kind of factors that tend to make a big difference here is both the number of classes that you're trying to differentiate, and then also how, just the classes themselves. Sometimes you'll have a few classes that you want to differentiate, but they're actually just not spectrally that's different, or maybe even occur in similar topographic positions. So, the number of classes and what those classes actually are tend to make a fairly large impact on this. One thing that hasn't made a big impact is whether we're doing a pixel level or an object-based classification. That tends to be not a big factor, especially at the moderate or Landsat scale, as opposed to some of these other factors. Just as a note, these images here, which I use as an example throughout the talk, this is a Canaan Valley, which is a plunging anticline in West Virginia. That's a pretty well-known wetland area and like nature preserve. And here you can see a leaf on image and a leaf off image, and you clearly see the differentiation there between some broad community types. So the spectral data we used in this study came from, again, the University of Maryland's Global Land Analysis and Discovery Laboratory. And specifically, we used their GLAD phenology type C metric set. This paper describes how those data are generated. And then they've been used in other projects that this group has pursued. Just as one example of that, though, this paper published in Remote Sensing Environment discusses how they use these metrics and the JEDI LiDAR data that's collected from the International Space Station to create canopy height or forest canopy height models for the entire globe. So these GLAD data sets became a feature space or the predictor variables used in those models for this specific task. Okay, so what are like these GLAD phenology metrics about? So the goal is basically to produce a set of metrics from 16-day composites of Landsat images that kind of capture the phenology, spectral variability, or just seasonality at a location. So their processing chain's kind of complex, but some of the key components are that first, they take the Landsat data that's available and they merge those into 16-day composites using the best available data based on, like cloud cover and whatnot. That will generate tiles that look something like this, where you're still going to have some clouds. You may have some gaps. Here you can see the stripping pattern from the scan line corrector error with the ETM Plus or on Landsat 7. So they're not perfect scenes, but they take the best data that's available over that 16-day period and aggregate it. Now, in order to go from this raw data well, it's not really raw data, go from these composites, I guess, to actual metrics, you have to pick a year that you're interested in. So for this study, we used 2019. And then you download all the 16-day tiles for that year that cover your extent, and then also all the tiles from the prior 4 years. And then you run these data through a Perl script, and what it goes through and aggregates the data. It does gap filling using the prior years if it has to, and if the prior years are still cloudy or there's gaps there, then it just linearly interpolates across missing pixels. So what you end up with is a data set that has a value at every location. And then from that data, they generate a large set of metrics that can go into predictive models. This is a table that kind of summarizes that metric set. Again, they have 3 different sets, A, B, and C. We use the C set because it's really aligned for differentiating things based on phenology. But basically the idea here is that it's a series of spectral band statistics from the time series of different normalized ratios between two bands, a set of parameters in which you're taking a value and normalizing it based on a corresponding variable. And they use a couple different here. It's basically the NDVI, shortwave versus near infrared, and then a brightness temperature, the thermal band. And then they also have some metrics associated with phenology. So like start of season, end of season, seasonal averages, seasonal amplitudes. Okay, so that was basically our spectral inputs, and there was a total of 188 of those that come in. In terms of the terrain data, we derived a series of metrics from the NED, or National Elevation Data Set 10-meter data, which were then subsequently aggregated up to the Landsat scale at 30 meters. So just a few examples here. We tried to incorporate measures that take into account the aspect and potentially incoming solar radiation and moisture at a location. So those include like the topographic radiation aspect index, the heat load index, the site exposure index. We also incorporated measures of just the shape of the surface, surface curvatures, dissection roughness, and measures of slope, like slope and elevation, and then local topographic position, like ridge versus valley. This is one of the areas I'm really interested in. I do a lot of work with DEMs and digital elevation data, and working with geomorphic and geohazard applications. Just last year, or I guess this year, Charlie Shobe, who's our geomorphologist here at WU, and I put together a review article on the use of these types of metrics in spatial predictive modeling. That was in Earth Science Reviews, and it's open access. It's open access if you're interested in looking at that. So anyway, what we ended up with was a feature space that incorporated spectral data and then also terrain characteristics. This is showing the average shortwave, near infrared, and green bands from the available data, but only from the first to the third quartile, so the average between the first and the third quartile. So you see here, you end up with an extent that's pretty cloud-free, but then there's actually been some gap filling and stuff applied to this. And this is showing a 3-band composite of topographic variables: slope, slope position, and surface site exposure index. And for the modeling component, we use the supervised classification process with random forest. Random forest is used a good bit these days. I don't know if it needs a lot of discussion, but effectively this is an ensemble decision tree method. So you're using a bunch of decision trees collectively as a single model. Instead of having each tree provided all the training data and all the predictor variables, you give each tree a subset of training data and a subset of predictor variables. And the goal here is to basically decorrelate the trees. So you have a set of weak classifiers that are collectively strong because they are not correlated with each other, and thus that should generate or reduce overfitting and potentially improve generalization. And then within the forest, all these different trees act as an ensemble, and then the majority vote determines the class. And also, just based on the distribution and proportions of the votes for each class, you can get back a probabilistic prediction or for each class that's summed to 1. We want to make some comparisons of how well these GLAD metrics will perform to other means to capture, summarize, or characterize the seasonality at a location. So we also calculated the summer band means for available summer images that were, not cloudy at the pixel location. So we had summer, fall, and spring band medians. The way we got those was we extracted all the Landsat data at those locations using Google Earth Engine and this Python library called GE subset. And then we filtered out the ones that were cloudy or had some type of quality flag issue. And then we aggregated them by seasons, and then got the medians. And then we also used that same data and fit a harmonic regression model through it with 3 harmonics. And we did that for the NDVI and the 3 tasseled cap transformations, brightness, greenness, and wetness. And then the set of coefficients in those models became a feature space that we could use to compare the GLAD output to. All right, so this is what we ended up with. This is a statewide forest cover map. Just some notes on some of the just to kind of standard pattern or general patterns across the state here. You know, in the state, we do have some spruce stands, but they're really only at high elevations. Historically, the extent of spruce stands were actually much wider, but that's been minimized because of logging and whatnot. So a lot of our spruce have been replaced with northern hardwoods. If you go out into the plateau, it's dominated by oak dominant stands in mixed mesophytic, and the dominant control there, other than anthropogenic changes, is the aspect which relates to insulation and moisture and whatnot. And then in the eastern part, we see a higher dominance of dry forest, oak hickory, oak pine forest, because it's just drier out in that part of the state. And then each of these classes has a subsequent probability surface associated with it. Now, in terms of like how well these types of predictions work, this is not an easy task. So you generally don't expect to get really high accuracies for these types of problems. So just as an example, when we differentiated 7 classes, just using the spectral data, we maxed out accuracies around like 55%. Which seems bad, and it kind of is. But if you think about this, and if you'd assume that these classes are evenly distributed or evenly proportioned, which they're not, but just assuming that, a null information rate would be like less than 20% because there's 7 classes. So, you know, there is some information content here, but it is difficult to do. So you don't really expect to have high accuracies. If we take our spectral data and we add in our terrain characteristics along with that, that increases it by 10, 11%. So that does highlight the value of having these additional terrain characteristics. And then we also looked at combining 2 classes that were heavily confused, specifically the oak hickory and the oak pine classes. You can see here they're pretty confused with each other based on the off diagonals here. So we merged those into a single like oak dominant class, and that increased the accuracy just by roughly 10%. So our highest accuracy with that 6 classes using the GLAD and terrain data was roughly 76%. So again, that kind of highlights the importance of what the class definitions are and what classes you're trying to differentiate. Another part of the methods was to, instead of just like subsetting the data into a training set and a testing set, running a model and then evaluating on the withheld data, we did this in like a bootstrap way where we would have a training set and a withheld test set, make a model, predict to the test set, then we would reshuffle it. So we'd have a different data partition, and we ran, I believe it was 50 replicates of each of the models. And that allowed us to get a distribution of the assessment metrics. And you can see we have several different assessment metrics here. What we found generally was the best performance was provided by the combination of terrain data and actually the harmonic regression coefficients. So the GLAD phenology metrics did a pretty good job, but they didn't perform to the level that the harmonic regression coefficients did. And also the feature space was much larger. So I think this highlights the value of these harmonic regression techniques for forest type differentiation and, you know, just characterizing phenology in a small set of predictor variables. So here were kind of the key findings from that study. Again, we found, similar to other studies, that digital terrain variables are really useful for this, for these types of differentiation, or for forest type differentiation, and mainly because a lot of these forest types are spectrally similar. So having unique topographic locations that they occur helps you differentiate them, even if they're somewhat spectrally similar. The number of classes and the definition of the classes have a fairly large impact. Again, we had some key classes that were very difficult to separate, and combining those helped. One issue is that we had classes that we definitely wanted to differentiate, but but they also intersected or overlap with other classes. A good example of that is mixed mesophytic. It tended to be confused heavily with the oak classes and even the northern hardwoods to a certain extent, but that's a very unique, like for community type versus a dry forest. So obviously you'd want to differentiate that. When you do have these problems where it's difficult to separate things or classify things in a very accurate way, these probabilistic outputs are actually really useful and are a good additional output to include. So, if you can't trust the hard classification because of the amount of error, then having the probabilistic predictions can help augment that a bit. So, for example, if we just looked at whether the correct class was in the top 3 probabilities, that would get that accuracies up to like over 90%. So I think that really highlights the value of these probabilistic outputs. And again, those GLAD phonology metrics that we investigated did a decent job, but they didn't perform to the level that our harmonic regression coefficients do. So I think there's a need for, in terms of like analysis ready products for the USGS, or I guess the Landsat program, USGS, whoever's curating the data to generate consistent harmonic regression surfaces that can be used for modeling. Moving forward with this, we're starting to do this in other locations, but instead of using our like state level surveys, we're using more consistent data that's available across the country, specifically the FIA data. So we're working with the FIA group, and they have this big map project, and we're doing some assessment of using some of the GLAD metrics inside of that workflow. So this is just some example outputs for Maine and Oregon, and here's some of the probabilistic surfaces for the forest types that were differentiated in Oregon specifically. Okay, so moving on, the second project is related to forest fire fuel mapping. This is, again, a project that was funded through the U.S. Forest Service, and we work closely with people at the Northern Research Station on this project. And instead of working at the scale of the entire state or the Landsat pixel resolution, 30-meter resolution, we're now looking at individual stands, and we're using point clouds as opposed to spectral data. This study specifically was conducted in the Pine Barrens section of New Jersey. The people in the Northern Research Station I work with work a lot in that area. So that's why we use that data. So specifically, we did a study in this fairly small management unit. And in these locations, they do prescribed burns. Some of them have been burned multiple times over the years. Some haven't been burned. So there's a good bit of variability. And we actually had we had pre-burn and post-burn scans for locations that were burned. So we were able to look at difference over time. So specifically, what we were trying to do with this data was to calculate or see how well we could estimate the composite burn index with metrics derived from the TLS data. If you're not familiar with the composite burn index, it's basically a field-based visual method where people look at sites pre-post burn, and they fill out some forms, make some measurements, and then they aggregate that into a unitless index that is supposed to correlate, or I guess correlate's the best word, the severity of a burn at a location. So basically our hypothesis here was that the changes in the forest structure could be captured in the TLS data, and thus the TLS data might be a good way to, maybe a way in the future to create a new way to assess the burn severity. So we specifically in this study used terrestrial laser scanners as opposed to aerial LiDAR. And more specifically, we used data from a Leica BLK360. And these units are cheap in terms of ground-based laser scanners. An analytical grade unit, they may run like $60,000 to like $100,000. These Leica units run around $20,000. They're basically push button units. You just go out, set them on a tripod, and push a button. So they're meant to be like really user friendly. So we specifically looked at using these units as opposed to a more analytical grade unit, because our goal was to assess this in the context of like operational mapping and monitoring in fire management. So having a cheap scanner that anyone could apply is kind of a prerequisite for that. Okay, so basically what we did was we took our TLS data, we ran it through a processing chain. So we started off with the raw data, we classified the ground points, we used the ground points to create a DTM, then we normalized the data relative to the DTM, so the Z became height above ground. And then we aggregated the data into height bins, and within those height bins, we calculated a bunch of summary metrics, mainly from the Z values or the elevation measurements or height measurements within the height bin. We also had RGB data because this unit collects some non-calibrated, non-analytical image data along with the points that are then associated with the point measurements. So from that, we calculated a couple visible band indices and included those into the calculation. So we ended up with a fairly large set of metrics that summarized or characterized the distribution of the points within the point cloud. And we did this just within like a 10-meter radius around the scanner or the plot center. And in order to look at change over time, we did this for the pre-burn scans and the post-burn scans, and then we differenced each of the metrics one by one. So we had a change in the metric as opposed to the metric itself. And then lastly, instead of doing like just the total CBI or burn index, we compared it to indices for different strata. So we looked at total, trees, shrubs, herbaceous layer, and then the substrate layer individually. And also, in order to generalize this a bit, we looked at multiple models. So we fit a model with a subset of the predictor variables that were selected using a feature selection process, using multiple linear regression and ordinary least squares type fit. We also fit random forest, but not in classification mode as in the prior study, but now we're using it in a regression context. So shouldn't really need to go over that again. And then lastly, we looked at support vector machines, which is boundary optimization type algorithm where it attempts to find the optimal hyperplane or separating boundary between data points, and that boundary is defined by the closest points to it, which are called the support vectors. Specifically, we implemented a radial basis function, SVM, since the boundaries were nonlinear, so we had the data had to be extrapolated to a higher dimensional space to get like a linear boundary or separation. Okay, so this is showing some of the results from that study. So again, we looked at multiple strata, so total burn index, trees, shrubs, just the herbaceous layer, and then the substrate layer. And we assessed the model using R-squared, which is not really an accuracy metric. It's just measure variability, or the measure of variability, or the proportion of variability explained. And then we also use RMSE. Now, because there's a different amount of like variability within each of the strata, and like the mean and standard deviation of the distribution is different, you really can't directly compare these RMSE values to each other across the strata. So lower RMSE is better, higher R-squared is better. So generally what we found was that using this differencing of the TLS metrics pre and post burn, we were able to get decent predictions or fits or correlations with CBI for the total CBI and for the trees only. The results for the shrubs were okay. We were getting like a 0.6 to 0.7 R-squared for that. And then it did a pretty poor job at estimating burn severity, specifically for the herbaceous layer or the substrate layer. And since this was looking at the three-dimensional structure of the point cloud as the primary input space, it would kind of make sense that herbaceous and substrate layers would not be well predicted, whereas the more vertically dispersed layers, the shrubs, trees, would be predicted better. Also, generally, we found that the random forest and the support vector machine models did a better job at this prediction process than the multiple linear regression did. And that was pretty consistent across the different strata. We also looked at some of the different feature spaces. So one issue with this method, if you were going to try to apply it in a practical way, is you would have to have data from before and after the burn. So that may not always be the case. So we also just looked at how well the models performed if we just gave it post-burn data as opposed to differencing the post-burn data with the pre-burn data. So kind of generally what we noted here, and each of these are just the different algorithms. The top one's random forest and SVM, and the last one is multiple regression. Generally, we saw slightly better performance if we did the differencing. But the post-burn did not do a terrible job, which is kind of good because that means that you could try to replicate this without having to have data before the fire, which you'd have to obviously plan ahead for that. Generally, the point cloud metrics did a better job than using just the metrics from the camera. That kind of makes sense. I mean, CBI is definitely correlated with the spectral signatures because of charring and whatnot, lack of green material. But that data is not very, it's not calibrated, so it's a not very analytical spectral information. So even though you'd expect correlation with burn severity, especially with change, you really wouldn't. You would probably expect some error because of just the lack of standardization or calibration. So another thing we looked at in this study was just the importance of different metrics. So one issue with this is you can generate tons and tons of metrics to try to summarize the point cloud for inclusion in the model. So you generally would probably want to, just for the sake of simplicity and to make simpler models, you would want to probably subset a feature space. So we looked at a couple different methods for assessing variable importance. The method here on the left is the Baruta method, which is based on random forest, and effectively you're comparing a metric to how it performs relative to a shadow variable, which is like a random noise variable. And then over here, this was a kind of more traditional random forest-based importance assessment using the conditional random forest methods after Strobel. One thing that's kind of interesting to note here is we did this in replicate using different subsets of the training data, and there actually is a substantial amount of variability in the result. So I think this highlights how variable importance can be a little bit misleading if you only run it like on one subset of the data or one training test split, because you're going to see some variability based on just the makeup of the data and whatnot. So I'm a big fan of, if you're doing this type of accuracy or variable importance quantification, to do it with multiple subsets and data splits to try to get a distribution as opposed to a single metric. Okay, so some key findings from this study was that, I think generally the TLS did a decent job of trying to predict CBI for trees and in total with, R squareds like over 0.9 when using machine learning methods. And even for the shrubs, we were getting like above 0.6, but it didn't do a great job for the lower strata, the herbaceous layers and the substrate, which kind of makes sense in this case. We did find that incorporating the RGB data helped the model perform better, but it didn't perform well on its own. So having the information on the Z or the heights summarized is very important. The camera data is helpful, but it's not a great supplement, or it's not a great on its own. So then the key thing that we're working towards here, and we're still kind of hoping to progress with this a bit more, is we feel that TLS has some benefits in that it's repeatable, it's pretty quantitative, it's a fairly fast assessment. You can scan a plot in generally like 5 minutes. It requires less field experience and expertise, and it's generally pretty flexible. So we're hoping that as we continue to play around with this in the future, we want to long-term get to a point where we can have like a burn severity metric that is purely based on like changes in TLS point clouds, as opposed to comparing it to an existing method that is based on like field observation. Well, that's a little ways down the road. Just kind of as a side note, there's a lot of practical interest in using these cheap, well, relatively cheap TLS scanners for ecological and fire-related forest management and monitoring. But there's still a lot of work that needs to be done in terms of best practices and figuring out how to use these things in a repeatable way. So just moving forward with this, some of the things we're looking at are to characterize the point cloud in different ways. So I'm really interested in this concept of making use of the geometry of the data collection in the way that it's actually summarized. So we're trying to build out methods that you can summarize the data using a spherical voxel space as opposed to like a square voxel space that where you can keep track of the pulses and actually figure out what areas were measured, what areas weren't measured or were occluded, and where there are gaps where there were no returns, such as canopy gaps. So we're kind of in the process of figuring out ways to do that. But one of the issues and complexities is that a lot of these scanners don't make available the pulses, the information about the pulses that actually didn't come back to the sensor. And I really think that to standardize these types of data, you want to be able to standardize against the number of pulses as opposed to the number of returns. So in a space, you might want to be able to say this volume had 100 pulses that went through it, and 21 of those pulses came back. It's almost like normalizing against like 100% reflectance. So anyway, that's something we're working with, but we keep coming up against technical issues where we just don't have access to enough metadata to do it. Okay, so to kind of wrap up, I wanted to kind of talk about these studies and like collectively and broadly in terms of some lessons that I've learned as I've started playing around with applying remotely sensed data for forest mapping and fire management and whatnot. Okay, so one of the issues we ran into a lot in both of these studies is the concept of having a very large feature space. Right, so you have a bunch of variables that you're going to use to make a prediction. Now, you would think that having a lot of variables would make for a better model because you're giving the model more information. But that's been shown to not always be the case. So there's this concept of the Hughes phenomenon or cursive dimensionality. And the idea is that as you increase the feature space, you're giving it more information, but you're also creating a much more complicated model or a complicated feature space. And that can result in decreases in accuracy, especially when you have a small set of training data. So you can see here with the 1,000 training patterns in this example paper here, they weren't really getting much of an improvement, but it really wasn't getting worse as they added features. In contrast, when they had 100 samples, then it actually got worse as it went along because you didn't have enough samples to characterize this really large feature space. Another just practical reason is to be able to create a more parsimonious model or just a simpler model to actually apply to new data. So determining the best features, augmenting the feature space, creating new features from existing features, those are all really important problems when you're wanting to eventually create a technique that could be applied in an operational manner. And a lot of the techniques we have for assessing variable importance, they have known flaws or known issues. So it's actually not a very easy problem to solve. Again, in terms of the algorithms that you're using, I've found consistently that machine learning is generally outperforming your traditional methods, your parametric methods like regression, logistic regression, maximum likelihood, things like that. But obviously, one of the trade-offs is having a more complicated model that's more of a black box. In terms of like what models are best in the context of within the space of just the machine learning models, that generally seems to be a very problem specific. It seems that like SVMs and random forest and maybe boosted decision trees like extreme gradient boosted trees, they're kind of the default techniques that people use now. but it's not really no guarantee that random forest is always going to outperform SVM or something. So generally we find that we have to do a comparison of these methods beforehand to decide on a method that we want to actually apply. In some of the studies that I do, I like to use multiple methods as just a means to generalize the results. But I'm trying to get away from doing studies where our goal is to just compare methods, because I think that's like been done at this point. One thing that I found really interested in our first study is just the level of variability that we saw in our models, just based on how we split the training and testing data. So again, we did that with multiple replicates. We did 50 of each feature space. And that allowed us to plot back a distribution. Here's a box plot of the assessment metrics when we predicted back to the testing data. And we could see variations on the scale of 5 or more percent based on the models. And that seemed to be more of an issue even when you had data or had a classification problem that was complex and the accuracy wasn't very high. So one thing I don't think we do a very good job of generally in remote sensing is putting error bounds around our assessment metrics and our, as part of our accuracy assessment. So one way to do that is by using, using some type of theoretical distribution, like a binomial distribution around your measurement. Another way to do it is like in a bootstrapping way, where you just run the model multiple times with different data subsets. But in short, I feel like that's really informative and actually gives you a better sense of model performance, because if you're seeing a fairly tight or fairly consistent performance, regardless of the input data, that might tell you something about the sensitivity of the model to the input space. Whereas if you have a lot of variability, that means that how you split your data can make a really big difference, and thus a single metric may not actually be that that informative. So error bounds around accuracy is an important topic, I think, that we don't do a lot in remote sensing. I'm really interested in accuracy assessment in general. So just this is kind of another side note. Last year, Tim Warner and I, who's my research advisor, who is an alumni from Purdue, and one of our grad student, Luis Andres Bulin, we put together a series of papers on best practices for accuracy assessment in the context of semantic segmentation, like deep learning and object detection deep learning. Because there's lots of weird complexities that arise from how deep learning pipelines work that I think introduces some issues in terms of doing accuracy assessment in a non-biased way that you're actually assessing generalization. There's also just a lot of discussion about the best metrics that we use to actually compare our models these days. Kappa, for example, has kind of went out of favor because it does have some known issues, and there's been other things that have been suggested, like quantity disagreement and allocation disagreement, or the map image classification efficacy measure. So I think that I think the important thing about accuracy assessment metrics is that you choose to use metrics that actually assess what you want to assess. So for example, if I'm interested in assessing the probabilistic output, not at a single threshold, but across multiple thresholds, it really makes sense to use a method that takes that into account, like the receiver operating characteristic curve or the precision recall curve. Whereas if you're looking at a hard classification, then a confusion matrix and its derivatives make a lot more sense in that case. Another thing that really matters and can be very misleading in the case of accuracy assessment is the relative proportion of the classes in the actual landscape. So lots of metrics are sensitive to class proportions. So for example, the PR curve is, the ROC curve isn't as much. So, and obviously the confusion matrix would be very different if you treat all the classes as balanced or equally abundant versus their true proportions. So I think that's another thing in remote sensing that we tend to not do well, is if we're reporting something like a map accuracy, it really should be based on class distribution that's proportional to the actual distribution on the landscape. Whereas if you have an equal number of test samples in each class, what you're really getting is like an average class accuracy, which doesn't really scale to a map if the proportions are different, which they likely are. This is a paper I really like. This is almost 15 years old now, but it's still really relevant. So this is from Giles Foodie. And he made an argument that a lot of the assessment methods that we use are inherently harsh in remote sensing, meaning that they assess the maps in a very spatially explicit way, and in a hard classification framework, where it makes sometimes our output seem maybe not as accurate or useful as it could be, right? So for example, in the world of forest type mapping, what I was doing with the first study was a hard classification with some probabilistic output. But when we did an assessment of the hard classification, we did it in such a way where we assumed that each of our locations map perfectly into one of the classes. But in reality, a lot of these classes are somewhat gradational, or you're going to have locations that don't fit cleanly into one of these classes, right? So for example, if you're like working your way around a hill slope in terms of the topographic aspect, there's going to probably be a transition from like a dry forest, like an oak dominant forest, into more mixed mesophytic forest on the wetter slopes. So so having that hill slope broke into two broad categories with no gradational component is a harsh way to assess it. So I think that's an important thing that we need to recognize when we do assessment in remote sensing. That's also one of the reasons why I'm a pretty big proponent of using and providing not just hard classification output, but probabilistic output as a final product. This is just a few examples. This is a project I worked on with the West Virginia GIS Tech Center, where we were looking at the likelihood of slope failures for the entire state. This was a product looking at the probability of occurrence of palustrin forested and palustrin emergent wetlands. And obviously this is one of the forest type examples. So I think there's a lot of information content in these types of outputs, especially when the thing that you're mapping is difficult to map accurately in terms of a hard classification. I think one of the things we struggle with, and this is something that I've noticed in applied mapping tasks that I've been involved with, if we give somebody a surface like this and say, this is your probability surface for slope failures, the first thing they generally ask is, where are the bad areas, right? So inherently, they want to go from a more continuous probabilistic output into a hard classification output or binned classification, which in many ways kind of defeats the purpose of even doing it that way. So that's something I've always struggled with, because I think there's information content here, but we really don't know how to use it or integrate it into actual applied mapping, modeling, or decision-making tasks. One of the problems that we continually run into in remote sensing, and I think is becoming even more of a problem, is the idea that most of the algorithms that we use to make predictions are supervised or empirical, where we're effectively learning from examples. So in our forest type mapping, our examples came from these field plots from the West Virginia Natural Heritage Program. For our CBI predictions, the training data came from field-based CBI measurements taken up in the New Jersey Pine Barrens. So without having that training data or labeled data, it's not really possible to implement a lot of the common methods that we use, like linear regression, machine learning classification, whatever. So that's become a bit of a bottleneck. And I think that that's even more true than it used to be because of deep learning. So if any of you work with deep learning, you may know that deep learning algorithms tend to be very data hungry. If you give them a small training set, they tend to overfit worse. There are some ways around that, like data augmentation or transfer learning or whatnot, but it is a known problem. And on kind of the other side of that, in remote sensing, we can generally come up with, it's a lot easier to come up with unlabeled data in a large abundance in some cases. So for example, if I wanted to do a study with Sentinel-2 images, I could easily find like tons of little extents that I could throw into a model, but labeling those extents become a much more daunting, time-consuming, expensive, or even in some cases impossible task. So I really am excited about some of the work that's going on with semi-supervised learning in our field, because this really is hopefully going to help solve a problem that's really plagued us, and that we don't always have access to the training data we need to train our models. It's kind of this chicken and egg problem. So in the world of deep learning, there's a lot of new methods that have come out over the last 5 or so years, where it's an augmented architecture where you can input labeled data, and then you can also input a large set of unlabeled data, which is used to train or regularize the model in some way. There's a ton of different methods. I feel that this is going to be a big part of our field in the future, and I'm looking forward to seeing where it goes. Unfortunately, I haven't gotten into this that much yet, but I am with my geomorphic mapping project. I'm hoping to get into this with my grad students in the next couple of years. But I see this problem all the time with all my work, and I feel like semi-supervised learning could help solve a lot of problems across our discipline. Okay, so that's everything that I had. Again, I really appreciated being invited. I felt honored that I was considered. If you're interested in contacting me, feel free. My email's here. You can always just look me up also. I also have a GitHub repo. It's not super exciting, but we do have some stuff for our projects. We have a YouTube channel, which we have like we're up to like 300 videos now. It's a lot of GIS, remote sensing, and like Python and R coding stuff. And then my current website is westvirginiaview.org. So again, that's a consortium that I'm currently running. If you go to that site, let me just show you that real quick. We have, let's see here. So this is our site here, West Virginia View. We have some links here for research stuff. So we have some data sets up and some links to our GitHub repos. The force type mapping project I talked about, we're going to put that data up. We just haven't done it yet. We have to get some permissions and stuff worked out, but our goal is to add that data set on here soon. And then we also have had projects over the last few years that are associated with course development. So we've developed these open, free courses that people can take and work through on a variety of geospatial topics. Our most recent one was a kind of introductory like data science course taught both in Python and R. You can choose your language. So it's just like a broad overview of like data science methods. We have courses on GIS, remote sensing, spatial analysis, web development, and web cartography. My open source spatial analytics class is an R course, so it's doing GIS and spatial analysis and spatial predictive modeling in R. And then this last class here is a short thing we're still adding to about geospatial deep learning using PyTorch and ArcGIS Pro. Okay, so that's everything I had. I'm happy to take any questions. If you don't feel like comfortable talking, I have the chat up on my other window, but you feel free to talk.
All right. Well, thank you, Aaron, for a very interesting presentation here. We have time for a few questions. So anyone, either just open your mic or just type in the chat.
Aaron, I have a quick question for you.
Yeah.
Firstly, this is a great talk. I really like the way you handle the data analysis, accuracy assessment seriously. So not so many people in remote sensing doing this work so seriously in these days. The forest mapping project you're doing, like similar to we are doing in southern Indiana. The landscape in southern Indiana is rough, but it's not no big mountains, but it's rough. I mean, so the slope is an important factor there. It's a small but steepy. One of the students is doing the species analysis. Slope plays the more important role than spectral information turn out. Then another thing is the data. We also use the state forest inventory data like you did for West Virginia. The location error is a problem. we have to use like a fine resolution data. Maybe the Landsat 30 meter is okay, not perfect to southern Indiana here. It's if you talk about half pixel registration error is about 15 meters. Then the plot error we are talking about up to 20 meters, maybe 25 meters sometimes. So mix these error together, then the accuracy cannot be that high when we do the training accuracy assessment with the reference data collected from the state. So how did you handle that issue here in your study, in your forest mapping project?
Yeah, so for our study, we worked at the Landsat scale, and so that gave us a little bit of wiggle room in terms of being in the Landsat pixel that we were interested in. The data that we were given does have a lot of it is post-processed GPS, and they have in the table like an error estimate. So we were able to do a little bit of skimming of features out from that. We did just some other kind of standard like GIS overlay to get rid of data points that we felt were non-trustworthy. So like at every location, we just grab like the NLCD category from like the, I don't know, like 2001 NLCD up. And if any of we would only use the point if it was mapped as forest in all of those data sets. And if it was mapped as something else, we threw it out, even if it was just one of them. We did have to make an assumption that once we did those types of filtering of the original data set, that if it was forest, if the error was a little higher than the Landsat scale, we were assuming that it was still within the same forest type. So that was a noted issue in our paper that when we published this. And I think that's actually one of the big issues with doing this in general. It's hard to find field data that's reliable, timely, and also like, spatially accurate, right? I think that's one of the nice things about maybe using the FIA plots, but if you've, I don't know if anyone's ever tried to get FIA data, it's like the worst process. It's awful. They consider it very private data, so you have to go through. It took me over a year to get access to FIA plots, for example, from the Forest Service. But those are actually generally referenced pretty well, but you have to get them from the Forest Service because they move them around. The public data set, the coordinates are actually wrong to protect privacy.
The accuracy you get 7 forest types, 76% overall accuracy. The mass value is 0.66, which is not bad, actually, for this kind of classification. And if you only refer to the mass value 0.66, is above satisfactory level, and can be translated into a standard, ordinary, the class distribution is around 90% overall accuracy if you make a conversion to that kind of eliminating the class imbalance effect. Actually, your classification accuracy is not that bad.
Yeah, I think that part of the, I guess in remote sensing, it seems like 80% is this like magic number, right? For like publishing, but that makes no sense at all because, if you have a complicated problem like this, I mean, that's potentially impossible. And if you're getting 80% accuracy on like differentiating force from everything else, that's like really bad, right? So sometimes I think those hard rules that have somehow became like benchmarks in the discipline are not helpful at all.
We have a question from Jinghua.
Thank you, Aaron, for the great presentation. For the first project that you worked on, you presented the work to do the first type mapping for the whole West Virginia and use the spectral data and elevation data. But I was checking the USGS 3D LiDAR program, and West Virginia is covered in 2018 with a pretty good point density. So do you have any plan to utilize that airborne LiDAR data set for that study as well?
Yeah, so we started this before the state's LiDAR was finished. It was just made available to our tech center has it now. We just got it like a year ago, and we have talked about that. We're doing there's a couple projects going on for geohazard mapping, general land cover mapping, and some of this forest type mapping, and we do intend to try to do some of this work again with those added inputs once we have time to do it. So in short answer is yes, but we didn't include it in this project because it didn't exist at the time, but it is there now.
So I do have a quick comment about your second project you presented. There's one of the professors here who is actually on this the Zoom call here, Dr. Ayman Habib. So this data that you presented here is from TLS, and you talk about the collisions. You're talking about the number of points in terms of density that come back towards the sensor and so on. The unit that he's building can resolve all these issues that you worry about, and also the speed in terms of data collection coverage, we can do much higher, much faster of data acquisition, resolving a lot of the issues that what you mentioned over there. So if you're interested, I think either I can help you connect or you can reach out to him directly. The question I have for you is, of these all the LiDAR metrics that you computed and correlated with the burning index that you did, have you ever considered about instead of directly working with the point cloud, working with a reconstructed product? Because by the end of the day, we do know it is not a point cloud, but it is like how big is a field in terms of like this is a 1 hour field, 100 hour field, or 1,000 hour field, right? All those things gonna matter. So have you guys done anything like that, or is the LiDAR that you have is the two course to reconstruct?
So not really part of that specific study, but it's part of like this wider Wi-Fi project that we're involved with, and we do some work with some of the Forest Service people in the Southeast. We've experimented with a bunch of different ways to try to generate metric sets, and one of those is using algorithms that try to filter out stems and tree trunks and differentiate fuels based on height and diameter, and then calculating metrics from like subsets of the point cloud that are likely to represent certain fuel types. That's still kind of an ongoing thing. We've had mixed success. Like certain things seem to, the algorithms that exist, at least for the type of TLS data we have, do all right. But then other things have just proven just very difficult to extract. For example, we've had a lot of hard time with like down coarse woody debris, which seems like it'd be potentially easy to separate, but it's just not easy to separate from everything else. So the short answer is that is something we're exploring with the people in the Forest Service group in the Southeast right now. One of the issues is there's just so many ways that you could summarize a point cloud. So coming up with this like optimal set is tricky. So we've experimented with this paper with just doing height-based, strata-based metrics. We're playing around with this summarization using spherical voxels, but we have done some work on trying to segment the point cloud into fuel categories and summarize that with some success, but limited success. I would really be interested in talking with your group about the scanner, because if so, I'll reach out.
Cool. And also just sort of the thing you mentioned about for the coarse woody debris and all that, we actually figured that out. So we do have an algorithm to do that.
Cool.
Yeah. Okay, any other questions?
I have one quick question. This is Ayman Habib. I have a question about like the point cloud. So so far you have been mainly relying on the TLS or the terrestrial scanner for the point cloud. And did you do any work with UEV based point clouds?
No, not yet. Like in New Jersey, in the Pine Barrens, there are areas where we have aerial and ground LiDAR. That the group I work with has done prior studies with ALS, but we haven't really done anything with UAV data to this point. I know with the TLS, it does a decent job with the sub canopy, but it's definitely not doing a good job at the canopy structure. Like so I think there is room for UAVs in that context for sure.
And a related question to the like, what do you think, based on what your experience with the TLS? I mean, I know that the TLS gives really dense point clouds, but what do you think in terms of the minimum number of points per square meter that would be useful for the analysis you are interested in doing?
Yeah, also I think that, well, for the work we were doing, I think the point density wasn't as much an issue as it is just the occlusion issues. You know, like, so there actually are like a fairly large extents, even in a small like 10-meter radius that you don't measure at all because it's behind a tree or whatnot. And that creates a lot of, you know, actually a good bit of data gaps. And obviously the way to like fill that and also increase the point density would be to use multiple scans, right, from multiple positions around the plot. But you do it, but which can be done, but there's some practical problems with that because it's not always easy to co-register them. And also if it's even a little windy, you get like, you know, if they're scanned separately and you try to merge them, the leaves will get doubled up, you know, it's because they moved a little bit between the scans because of the wind. So I think an optimal solution would be to have increased density, but also have multiple scan positions that are all co-registered into one cloud. So you minimize the area of occlusion. But again, there's like practical issues with that in terms of, you know, movement between scans and the accuracy of the co-registration.
Maybe I should apologize. Maybe my question was not clear. So my question is that, like, other than the occlusion, which is quite an obvious problem. So in area which you had it captured by the TLS, like, can you go down with the resolution and still have good products? So I'm talking about reducing the resolution.
Yeah, there's been a couple studies that have looked at that. We just use kind of the standard scan density with this BLK thing for this study, but there's a study by Atkinson, I can't remember the group, but they had looked at reducing the resolution of the point cloud, and they did get like noticeable decreases in accuracy in terms of what they were trying to predict. They were mainly looking at canopy related stuff like stem densities and stuff, but I can't remember what number they came up with, but they did suggest like a minimal point density for that problem. That's a really vague answer. I guess my short answer is that there have been some studies that have looked at that, but we haven't for this specific study.
Thank you very much.
All right. Well, any further questions? Okay, hearing none. Thank you. Thank you, Aaron, again for the wonderful presentation and very engaging discussion here. And yeah, if I'm really looking forward for, you know, potential collaboration with you and this group. So feel free to reach out. Okay.
Yeah, I appreciate it. Thanks again for inviting me. Hope it was useful or interesting.
Okay. Thank you everyone for participating, and we'll talk to you next week.